Welcome, explorers of the cosmos and those curious about science. Today, we will delve into the deep mysteries of the universe, where the boundaries between the known and the unknown intertwine in an intriguing game of paradoxes and discoveries. Get ready for a fascinating journey, where quantum theory and general relativity collide, and black holes reveal secrets that challenge our most fundamental understanding of reality. So without further ado, let's get to the video. The fundamental theories of physics, quantum theory, and general relativity are successful in their own domains, but they conflict when applied to extreme conditions, such as those close to the singularity of a black hole. General relativity suggests that information falling into a black hole is lost forever at the singularity, which conflicts with quantum theory's principle of conservation of information. The discovery of Hawking radiation indicated that black holes are not completely black and emit quantum particles due to quantum effects near the event horizon. This Hawking radiation raised profound questions about the relationship between classical gravity and quantum phenomena. Recent research suggests that information lost in black holes can somehow be recovered, challenging the previous view that information is irretrievably destroyed. The possibility of recovering information from black holes suggests that there are important quantum aspects to the fundamental nature of gravity. This raises the prospect of a quantum theory of gravity, where space and time emerge from more fundamental quantum phenomena. Black holes, by challenging the boundaries between classical gravity and quantum theory, may provide crucial clues to the search for a unified theory that encompasses both perspectives. The event horizon is the boundary of a black hole, beyond which neither light nor any other form of radiation can escape due to intense gravity. It is the point of no return, where the escape velocity required to overcome gravity is equal to the speed of light. In the classical view of physics, once something crosses the event horizon and enters the black hole, that information and matter is considered lost forever in the singularity. The event horizon creates a conflict with the fundamental principles of quantum theory, which states that information cannot be destroyed. This has led to the so-called black hole information paradox. The discovery of Hawking radiation suggested that, due to quantum effects near the event horizon, black holes are not completely black and emit quantum particles. This challenges the classical view that nothing can escape a black hole. The crucial question is whether the information that falls into the black hole is irretrievably lost or whether it can somehow be recovered. Resolving this dilemma challenges our current understanding of the relationship between gravity and quantum mechanics. The event horizon, by challenging our traditional conceptions, provides a window to investigate the interaction between gravity and quantum phenomena, leading to the search for a quantum theory of gravity. Studying the event horizon not only challenges established paradigms, but also leads us to explore new frontiers in understanding the fundamental nature of the universe. The history of the concept of black holes dates back to the 1780s to 1790s. During this period, two thinkers, the clergyman Jean Michel and the French mathematician Pierre-Simon Laplace, apparently independently, began to explore the idea related to what is called escape velocity. Escape velocity is the speed required to overcome the gravitational pull of an object and escape its pull. For example, at the Earth's surface, the escape velocity is about 11 kilometers per s. If an object reaches or exceeds this speed, it can escape Earth's gravity. Michel and Laplace began to explore the possibility of stars so massive that the escape velocity at their surfaces would exceed the speed of light. They imagined the existence of stars massive enough that the gravity on their surfaces was so intense that the escape velocity exceeded the speed of light. The theoretical consequence of this idea was fascinating. If a star were large enough to have an escape velocity greater than the speed of light, it would become invisible to outside observers. The light emitted by the star would not be able to escape its gravitational pull, making it effectively invisible in the cosmos. Although the term black hole was not used at the time, fundamental ideas about the existence of objects so massive that not even light could escape them began to be explored. The term black hole was coined later in the 20th century to describe this concept. The idea of escape velocity is related to the ability of an object to overcome the gravitational force of a celestial body and escape into space. This idea is fundamental to understanding the formation of black holes. The escape velocity of an object relative to a celestial body, such as a planet or star, is the minimum speed necessary for the object to escape the gravitational influence of that body without being pulled back. The relationship with the formation of black holes is related to the idea that if the mass of an object is concentrated in a small enough volume, the escape velocity required to escape that object's gravity can exceed the speed of light. This is crucial because, according to Einstein's theory of general relativity, nothing can move faster than light. Therefore, if the escape velocity exceeds the speed of light, nothing, not even light, can escape, and this defines a black hole. The initial idea, as mentioned in the transcript, came when scientists like Mitchell and Laplace considered very massive stars, wondering if the escape velocity of these stars could exceed the speed of light. If this happened, the star would no longer be visible, as the light emitted by it could not escape the gravitational pull. Black holes are therefore objects whose mass is so concentrated in such a small volume that the escape velocity reaches relativistic values, leading to the formation of an event horizon. This event horizon is an imaginary surface beyond which nothing can escape the black hole's gravity, making it invisible to outside observers. The event horizon is an imaginary surface that marks the limit beyond which nothing can escape the black hole's intense gravity. Once anything, including light, passes this point, there is no return possible. From an external point of view, the event horizon is an apparent boundary beyond which any object or information is lost to external observers. This leads to the idea that the black hole swallows everything that crosses its event horizon. According to Einstein's theory of general relativity, the center of a black hole is a point of infinite density called a singularity. However, the exact nature of this singularity is unknown and represents an area of uncertainty in the theory. In addition to the singularity, there are conceptual problems that emerge when considering the interaction between quantum theory and gravity. Specifically, there is a reference to the black hole information paradox, which involves questions about whether information that enters a black hole is completely lost or can be recovered somehow. The black hole information paradox, which arises from the interaction between quantum theory and gravity. According to quantum theory, information is always conserved, which means that if you know every detail about a system, you can theoretically go back and reconstruct the initial state of that system. Doubt about the conservation of information. The paradox manifests itself when information from particles that fall into a black hole appears to be lost, since, according to general relativity, everything that enters a black hole appears to be sucked into it. A singularity where the known laws of physics can break. Profound implications. Resolving this paradox has profound implications for fundamental understanding of the nature of information and reality. The initial idea was that information that fell into a black hole was irretrievably lost, which would violate the fundamental principles of quantum theory. Currently, the prevailing view is that information is not irreversibly lost in a black hole. Hawking radiation implies that black holes are not completely eternal, and that information can be encoded in the radiation emitted during the black hole evaporation process. The black hole information paradox arises from the apparent irreversible loss of information about particles that fall into a black hole, which appears to violate the principles of quantum theory, which require the conservation of information. The suggestion that information can be recovered from black holes comes from more detailed analysis of Hawking radiation. If the radiation contains information about the particles that fell into the black hole theoretically, this information can be recovered by analyzing the radiation emitted during the black hole's evaporation process. A key idea is that quantumly entangled particles can carry correlated information, even when one of them falls into the black hole. This implies that information about what entered the black hole can be encoded in the escaping Hawking radiation. The specific nature of how this information retrieval occurs is an active area of research and debate in theoretical physics. There are several proposals and conjectures, including the idea that information is preserved in Hawking radiation in some way. Despite conceptual advances, fully resolving the black hole information paradox is still an open challenge in physics. The precise nature of the relationship between Hawking radiation and lost information has not yet been fully clarified. The suggestion is that space and time are not fundamental entities, but emerge from deeper quantum phenomena. Rather than being fundamental blocks of reality, they can be understood as properties that arise from more basic interactions. The search for a theory that unifies quantum theory and the theory of general relativity is often called the quantum theory of gravity. Black holes, with their previously discussed quantum properties, play an important role in this context. The mention of quantum entanglement suggests that quantum phenomena like this may play a fundamental role in the structure of space and time. Quantum entanglement is a property in which two particles are so correlated that the state of one of them instantly determines the state of the other, regardless of the distance between them. The underlying idea is that a deeper, as yet unknown theory can describe the nature of reality on a fundamental scale. This theory could be so fundamental that space and time would no longer be considered as basic blocks, but would arise in a way analogous to quantum entanglement or other quantum phenomena. The mention of singularity in the text may be related to the fact that in the equations of general relativity, black holes are described by singularities which are points of infinite density. Understanding the nature of the singularity is a fundamental challenge in the search for a quantum theory of gravity. The discussion about the emergence of space and time from quantum phenomena highlights the complexity of the problem and the challenges involved in understanding the fundamental structures of reality. The fundamental theories that describe the universe, such as Einstein's theory of general relativity and quantum theory, are deeply tied to the nature of space and time. To understand how the universe behaves on cosmic and quantum scales, it is essential to have a solid understanding of these concepts. The question about the origin of the universe is intrinsically linked to the understanding of space and time. To discuss whether the universe had a beginning, whether it is eternal, or whether it went through significant events like the Big Bang, it is necessary to understand how space and time relate to each other in these extreme circumstances. The nature of time is a crucial part of this discussion. Understanding whether time is absolute or relative, whether it has a defined direction or can be reversed, directly influences theories about the beginning of the universe. Space and time are intertwined with matter and energy in the context of the theory of general relativity. Understanding how matter and energy influence the geometry of space-time is vital for modeling the evolution of the universe. Events such as black holes, singularities, and the behavior of the universe on subatomic scales require an advanced understanding of the relationship between space and time. These extreme phenomena are crucial to understanding the limits of our current physical theories. The search for a unified theory that integrates quantum theory and the theory of gravity, often referred to as the quantum theory of gravity, requires a deep understanding of the nature of space and time. This theory seeks to explain extreme events, such as the singularity in a black hole or the Big Bang itself. Understanding space and time also allows us to address broader philosophical questions about the nature of reality, causality, and the relationship between the observer and the observed. In short, the intersection between quantum theory and general relativity, especially when applied to extreme phenomena like black holes, presents fascinating challenges and profound questions about the fundamental nature of the universe. The information paradox in black holes, although persistent, has been confronted with the intriguing discovery of Hawking radiation, suggesting the possibility that apparently lost information can be recovered. The search for a quantum theory of gravity, which unifies the laws of physics on cosmic and quantum scales, continues to be a crucial field of research. The suggestion that space and time can emerge from deeper quantum phenomena opens doors to a deeper understanding of the fundamental structure of reality. Thus, improved understanding of the relationship between space, time, and the fundamental laws of physics not only enables us to decipher the enigmas of black holes, but also sheds light on broader questions about the nature of reality and our role as observers in this vast cosmos. So if you like the content, please smash that like button and subscribe so you don't miss the next videos. Bye!